Hello everyone. Today we are going to do some properties of continuous functions and which are used frequently. I start from here, that is the theorem composition of two continuous function is also a continuous. So first of all we have to take two functions, then such that their composition are defined. Two types of composition are there. We may discuss either Fogg or Goff. It depends on. So let's start the proof. In proof, first we have to fix the function. So we take let f and g be two functions. There is a restriction. We are supposed to deal with composition, so we write such that their composition exists. We deal only one composition. It is not required to prove both. Such that Goff exists. What does it mean? It means that is the range of the function f is a subset of, that is, domain of the function g. This is required if it is defined. Okay, so this is the position. Now let's take the point. In which way we take the point? So I start, let a be any arbitrary point in the domain of f. Since we deal with f composition g, that's why we take a domain of f. If we take, that is, g composition f, then we take a as a element of domain of f. Okay, so if a is the element of domain of f, so it implies f of a is the element of range of f. It also implies fa is the element of, that is, domain of g. So this is position. So f is continuous at x equal to a and g is continuous at fa. This is the situation. So we are supposed to prove f composition g is continuous. So what's our way to start here? F is continuous at a. It implies, that is, limit x tends to a, fx is equal to f of a. At the same time, g is continuous at, so we write, that is, limit, what's the old function? Here we are supposed to g, take g, so take it g y. And what's about the point? It is fa, so that's why we write y tends to, that is, f a is equal to, that is, g then f a. It is by the definition of continuity. So it implies, that is, what is y? Y is equal to fx. So we put here fx tends to fa, then g, then what's about the y? Again it is fx. It is equal to g, then fa. Here we write, since y is equal to fx, also x tends to a implies fx tends to fa. So here we may use, if fx tends to fa, so it implies, that is, limit x tends to a. This is the change by this property. Then it is g, then fx, it is equal to, that is, g, then of. Okay, now it can be written as, it implies, that is, limit x tends to a, f composition G, it is equal to again F composition. Therefore F composition G is continuous. This is the way to prove, that is how the composition of two continuous functions also is continuous. Similarly, we use to prove, that is G composition F, to prove it continuous. Here it is required to prove any one, and we may directly use as a result, as a property of continuous functions. Next one is sine function is, that is everywhere continuous. This is required to prove. So this is about proof. Let function f is defined as, that is sin x. Let a be any arbitrary point. Okay, now we are required to prove the function is continuous at point A. So we find first left hand limit, right hand limit, then the value of the function. So I start here, limit x tends to A from left. Then this is function. By rule, we change it as h tends to 0. At the place of x, we write, that is the point is A. In case of left hand limit, it is minus h. Since fx equal to sin x, so we write it is equal to h tends to 0 sin, then a minus h. Directly we use the formula. What is sin a minus b? Actually sin a minus b is, that is limit h tends to 0 sin a cosine h minus cos a sin h. Now we separate the limit. It is equal to limit, or just take out the constant. Sin a is constant, it do not depend on h. That's why limit x tends to 0 cos h minus, it is constant, limit h tends to 0, then sin h. It may written as, that is sin a into 1 minus cos a into 0. Now we get it is equal to sin a. So left hand limit at a is equal to sin a. Now similarly, ways to get the right hand limit. For right hand limit, I start, that is limit x tends to a from right, fx is equal to, v is same, replacing x by h tends to 0. Now x is replaced by the point plus h. Very simply we write it is equal to limit h tends to 0. Function is fx equal to sin x, so that's why we get sin a plus h. It is equal to limit, that is sin a cos h plus cos e sin h. Okay, now it is equal to sin a into 1 plus cos e into 0. It is again equal to sin. This is about right hand limit x tends to a from right fx. Also f of a equal to what? Sin a. Since f of x equal to sin x, then f of a equal to sin a. Then we write, since right hand limit at a equal to left hand limit at a, and it is equal to the value of function at a, therefore sin x is continuous at a. Since a is taken as arbitrary point, that's why sin x is everywhere continuous. For all real numbers, it is a continuous function. Next function is, we are going to deal exponential functions. In exponential function, I wish to take, that is, let fx is equal to a power x, where a is greater than 0. Again, we wish to prove it continuous, everywhere continuous. So let, here a is already used, so just take some other point. Let c be any arbitrary real number. Again we get left hand side limit, right hand, and so limit x tends to c from, it is equal to limit h tends to 0 f of, that is, c minus h, the point minus h, and it is equal to, that is, limit h tends to 0. If fx equal to a power x, then fc minus h equal to a power c minus h. It may written as limit h tends to 0 a power c into a power minus h. The same thing is written as limit h tends to 0 a power c, then 1 by a power h. Now it is equal to a power c, then limit h tends to 0 1 by a power h. Putting a power 0, we get 1, so a power c into 1 equal to a power c. Similarly, we get, that is, limit x tends to c from right, fx is equal to limit h tends to 0 f of the point c and plus h, and it comes as, it is equal to limit h tends to 0 a power c plus h, and it is equal to limit h tends to 0 a power c into a power h, and equal to a power c into 1 equal to a power c. Also, f of c is equal to a power c. Then we write, since limit x tends to c from left is equal to limit x tends to c from right, and it is equal to the value of the function at c. Therefore, f is continuous. It implies a power x is everywhere continuous. In a similar way, we can prove identity function is everywhere continuous, constant function, polynomial, rational function, cosine function, then tan function, logarithmic function. By the same way, we prove all are continuous. Okay.